Everyone.
So hello everyone and welcome back to the cycle of seminars of the astronomy department of IAG. The speaker of the week is Dr. Gary Mamon, and thank you Gary for accepting our invitation. This is really appreciated. And Gary got his PhD at Princeton University in the US and is now a senior astronomer at the Institut d'Astrophysique de Paris in France. And today Gary is going to present the seminar What Lurks in the Course of Globular Clusters, White Dwarfs, Black Holes, or Nothing? So questions will be asked after the presentation. If you are following the seminar from our YouTube channel, you can write down your questions in the chat and they will be redirected to Gary by the end of the talk. And before the seminar begins, I would like to ask everyone here at Google Meet to please turn off your microphones and your cameras. And Gary, you can start whenever you're ready.
Okay, well, thank you very much. It's a pleasure to be back in Sao Paulo, even though, to be honest, nothing is worth being in Sao Paulo for real, right? So I had the pleasure of being here in Sao Paulo for the SAB meeting of 2017. That was the last time. And before that, I had visited Eduardo Gastão, in 20 years ago, 2 years in a row. So today I'm going to speak about globular clusters, which is a new field to me. Right, so globular clusters are these amazing systems, quite spherical. There's amazing stellar systems around galaxies, including our own. And I'm a dynamical modeler, and I like to try to measure the mass profiles of, and the orbits of systems by their motions, internal motions. I'll talk to you about that. And when Gaia was announced, I thought, we should prepare for Gaia because there's going to be a revolution in the data. So that's why, that's what motivated us. And the idea was, could there be intermediate mass black holes in globular clusters? So these are the people who we worked with, and in particular, Eduardo Vitral, who is from Brazil. So he studied at IAT, I think, an aeronautical university, which is very prestigious in San Jose dos Campos. And then we also collaborated later with these three other people, Carl Kremer, Mattia Libralato, and Andrea Bellini. So, we know
Gary, the slide is frozen.
My slide is frozen. So I just
we are actually seeing the first slide.
Oh, I just pushed the second one. How did you know that I pushed them? Okay. So let me go back to the first one. Now I go back to the second one. Do you see the second one?
We are seeing a slide about LIGO results.
Yes, that's good. That's good.
Perfect.
So, so we now know the existence for sure of stellar mass black holes, thanks to the gravitational waves that are emitted when stellar mass black holes merge. And we know for sure that the existence of supermassive black holes because we see them through VLBI observations. Okay. And so the question is, are there intermediate mass black holes in between, okay, which is the masses of a few hundred solar masses to a few thousands or tens of thousands of solar masses? And one place where they might be would be the centers of globular clusters. If you just use the proportionality scaling relations between the black hole mass and system mass, you would expect that globular clusters would host intermediate mass black holes. Do you see the next slide? Number
yes,
3?
we do.
So in dwarf galaxies, we have some evidence for intermediate mass black holes because a few dwarf galaxies show AGN features. Maybe it's 10% of the dwarf galaxies. In globular clusters, it's a subject of debate, which we will add to. Okay, so people don't agree with one another. And the question is, we need better modeling and we need better data. Okay, so let me talk to you about the modeling. So this is something I've been doing for years. Since I was a master's student, I started doing this with a postdoc called James Binney. And basically, to do the mass modeling, we start from the 6-dimensional distribution in the distribution function 6-dimensional space. And this distribution function is understood to be incompressible And so you can write the compressibility equation called the collisionist-Boltzmann equation, or Vlasov equation. And because it's difficult to think in 6D, we think in 3 dimensions. And so we integrate over we take the velocity moment of the collisionist-Boltzmann equation, and we get the local dynamical equilibrium equation called the Jeans equation, which basically says that the divergence of a pressure tensor is the gravitational potential times the density of your tracer with a minus sign. And this pressure is the density of your tracer times its velocity dispersion squared. So this equation, the Jeans equation, was originally found by Maxwell, but it's called the Jeans equation because Maxwell already had his equations. So physically, what this means is that if you consider, say, a shell of matter, it's attracted to the center of its system by gravity, but the motions inside the shell, or at smaller radii than the shell, have a higher dynamical pressure than outside. So this difference of pressure will counteract the gravity. So this is the equation of hydrostatic equilibrium, if you wish, that people use in clusters of galaxies. So we use the same in dynamical systems, with the exception, and I'll show this in the next slide, that when you go to spherical symmetry, it's maybe easier to see, is that in contrast with the equations for gas, there's a second term in the dynamical pressure, which is the velocity anisotropy. In other words, the pressure tensor is not scalar. Okay, it's a tensor. Okay, and so in spherical symmetry, it can reduce to this parameter called beta, which measures the velocity anisotropy, which you can see 1 minus ratio of velocity dispersions in the tangential and the radial components. So beta describes to us the shapes of the orbits, whether you have radial orbits or circular orbits or random isotropic orbits. Okay, and because we have 2 unknowns in this Jeans equation and 1 equation, we basically have a mass anisotropy degeneracy, which might drive us mad. But in fact, there are ways to lift this degeneracy. Oops. Oh no. So sorry about that. Here we go. Do you see my slide 7?
Yes.
Yes.
Good. Sorry. So let me talk about geometry and dimensionality. So if we're considering just redshifts, we have line of sight velocities, and so we have 2 dimensions on the sky and 1 dimension in velocity space. But we put together the 2 dimensions on the sky to make it just a projected distance from the center, which I'll call projected radius. So we have 2 dimensions. If you have proper motions only, then you have 3 dimensions. And if you have line of sight plus proper motions, or line of sight plus plane of sky data, then you have 4 dimensions. So it's very rich to include Gaia data to model globular clusters, all right, because you gain 2 dimensions. It's just marvelous. Now, so here's an illustration with just 1 dimension, line of sight, and basically, the wider the dispersion of the velocities, the more mass you have, except that you have a projected view, and the mass is difficult to relate the projected view from the 3-dimensional view, but it's possible. Okay, and furthermore, the second component is that the distribution of the line of sight velocities is not Gaussian. Okay, and the shape of it indicates the velocity anisotropy for a non-rotating system. For a rotating system, it's completely messed up. Okay, so to go from the distribution function, you can take a triple integral of the distribution function to get the distribution of projected phase space. So that's a clean way of doing things, but it's very slow to do triple integrals. And you have to know what the distribution function is, but now we think we know what it is. We know what the family is. So I'm being lazy. I don't like to do triple integrals, so I found a way to express the distribution, the probability of the distribution in this projected phase space as a single integral, but I had to make one assumption, okay? And the assumption is that the local velocity distribution function, this little h in the equations, is itself a Gaussian. Not the line of sight distribution function, which I mentioned before, which is integrated along the line of sight, but just a local distribution function, okay? At one depth along the line of sight. And this, so it's a Gaussian, we know how to express its variance, and we know how to calculate the radial velocity dispersion by assuming a mass profile and a beta profile. We can invert the Jeans equation, so we know the radial velocity dispersion, sigma r, and then we can calculate everything, and we can do this in a completely Bayesian way, which is what we do. And it's very fast, so it's 1,000 times faster than doing the triple integrals. Okay, and then we can handle a field star component, okay, and we can work in higher dimensions, okay. So recently I generalized MAMPOSSt, this method that I've been developing in 2013. I generalized it to MAMPOSSt proper motions, okay, to handle both line of sight and proper motion data, and with a globular cluster component and a field star component. Okay, so it's very much the same thing. Okay, and so we can write the same type of equations for the distribution of a globular cluster in stars in projected phase space. And again, so we assume that the local velocity distribution function is separable along the 3 axes, and that each one is a Gaussian. So we have a separable Gaussian. This assumption is not exactly correct, but it works very well. And we've tested this, and I will show you in a second. Okay, and then we know how to express these velocity dispersions that we observe, line of sight, plane of sky radial, plane of sky tangential. We know how to express them in terms of our assumed quantities. And then, as I say, we can invert the Jeans equation. So, MAMPOSSt has done very well in a recent challenge of mass and anisotropic radial profiles of mass density rho and velocity anisotropy beta. This is a compact way of writing beta, which goes from circular at -1 to 1 at radial instead of -infinity to 1. Okay. And so MAMPOSSt is in blue, and the people I was comparing to here, the people we compared to, were all extraordinarily brilliant people, and they came up with very clever methods. And so one of the methods, the green method, did not work well because they assume that the line of sight velocity distribution function is Gaussian, and I told you no, that it has the anisotropy coded in it. Okay, so whereas MAMPOSSt is not as bad because it says that the local velocity distribution function is Gaussian. Okay, so it worked very well for density profiles and velocity anisotropy profiles. This is a case with line of sight only data, and when you add proper motions, I'll go back and forth. The match is much better. Okay, actually, MAMPOSSt is not doing so well inside for the velocity anisotropy. Okay. So now let's look at the data. So for those of you who don't know, when we look at a proper motion of a star in the sky, there are several components. One is the proper motion itself. So when we look at the motion, there's the proper motion itself, which is on the short time scales that we're looking at. It's first order, it's linear. Then there's there's a parallax due to the motion of the Earth around the sun. And then there could be other perturbations from planets orbiting around the star, okay, which also give extra cycles at different frequencies. Now, which globular clusters are best? So for this, we want to minimize the errors and to relative to the velocity dispersion. So we want to minimize the distance over the velocity dispersion because the errors scale as the distance. And so we chose the globular clusters that minimize these variables, and we threw out those which are rotating, because MAMPOSSt only works in spherical symmetry with no rotation. Okay, when you have rotation, you have flattening, and you need to know what your rotation law, and you need to know what your inclination is of the flattening, and you need to know what is the angle between the line of sight and the major axis. So it's complicated. So it's better to work with spherical systems, and there are such globular clusters. So I'm going to start with one of them, which is the second closest, NGC 6397. So the data is that we had 40,000 proper motions with Gaia up to 1 degree. And then we got 13,000 proper motions from the Hubble Space Telescope people, and they're much more precise, as I'll show you in a second. And we also added 7,000 line-of-sight velocities from the MUSE instrument on the BLT. Okay. So in this plot, we can compare the errors on velocity on the left or on the proper motion on the right for those which are proper motions for the four instruments. Now, of course, Muse is not proper motion; it's just line of sight. And so so it's more interesting to look on the left. And so you can see that, of course, as a function of magnitude, as you go to fainter magnitudes, the data gets much worse. And the black line is 1/2
Excuse
velocity
me, Gary.
dispersion. Yes?
What slide are you showing now?
18.
18. Maybe it's my screen, but I see the 17.
No,
We are seeing
also.
17.
We are at 17, but I was doubting if it was my connection.
And now?
Not yet. Maybe you have to stop sharing and start sharing again. It will
Okay, let's do that.
Thank you.
Do you see 18 here?
Yes.
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 Thank you.
Okay. 18 again?
Perfect.
Yeah.
Yes.
Okay. Sorry about that. And so what we see here is that the HST data has a more accurate proper motions than the Gaia data or the line of sight velocities from Muse, which are roughly like the Gaia. And the Gaia also has its own line of sight velocity. This is Gaia DR2. And now, later I'll talk about the more recent release. And the line of sight velocities from Gaia are completely useless at this point, okay? And then what we do is that we only have HST in the inner regions. So we use HST in the inner regions and we use Gaia far out. And because we need to go far out. Because even if we're interested in what's going on in the center, when we look at the center of the cluster, we're actually picking a line of sight, which includes cluster stars that are also in front and behind. So we need to know what's going on. And by spherical symmetry, by looking on the outskirts with Gaia, we can understand what's going on in front and behind the center. Okay. So now I'm on slide 19. I hope you see this. So we need to clean the data.
Yeah, we are seeing 18 actually, Gary. I don't know why.
These figures are too big, that's why.
Yeah, perhaps.
They're too heavy. Sorry.
Now it's 19.
Even my computer cannot handle this, okay? So we first cut in proper motion space. So in proper motion, there's a big separation between the field stars, which are in the upper part, and the globular cluster stars, which are in the lower part. And we take a very liberal cut because we don't want to throw away, it's better to be liberal, because if we're not liberal, if we're conservative, we'll throw away high velocity stars that are moving fast and might be affected by an intermediate mass black hole at the center. Then, now I'm slide 20. I think you should see this.
Yes.
And so now we filter in color magnitude space after filtering in proper motion space, okay? And so we reject those stars that are far away from the locus. And then we have a final data set, which is almost 10,000 stars, okay? And then we stitch, so one thing we need to do is we need to know the number density profile of stars, because that enters this, it was this new parameter in the genes equation. So we get this from deprojecting the surface density profile. But for the surface density profile, we don't use all the data. We don't use the data for which we have proper motions. We use all the data because it's more complete inside. Okay, and we found that the Sursich model fits best. So this is just to show you that we did many models and we did Bayesian evidence. I'm just going to skip that. This plot, so this corner plot that you may or may not see, slide 23, shows you that we did Markov chain Monte Carlo, and I'll skip that. So now I get to slide 24, mass orbit modeling results.
We are seeing 23.
Okay, so I'll skip and come back. I'm on slide 25. So velocities appear to be isotropic. So the beta parameter is consistent with 0, both for a single population. We also tried 2 populations, separating the bright and the faint stars, which might be segregated in the projected phase space. So we also tried separating them. And so there's no need for velocity anisotropy. So now so the question is, do we expect isotropy? And so yes, in the center we expect isotropy because the two-body relaxation times are short in globular clusters compared to any other astronomical objects, so except open clusters. So we expect that the stars will forget their initial conditions by by frequent encounters with other stars where they will exchange energy and they'll forget their directions. On the outer parts, people expect to have radial orbits. And indeed, this was confirmed by a less sophisticated mass orbiting modeling by Laura Watkins, where she finds that parts of globular clusters that are in regions of short relaxation time are isotropic, whereas other parts, which are where the relaxation time is long, are more radial. This is a very beautiful result. And then there's the effect of passages through the Milky Way. So this will cause more isotropy. I need to move on. So now I'm going to assume isotropic orbits. And so here are the results. So our reference model, number 7, is that we have no excess inner mass. And then when we put an intermediate mass black hole, we find a much higher improvement in the...
Gary, I think that you are in the slide 27, no?
Ah, okay.
You are seeing the 26.
Okay. I've never had such problems before. Okay, now I'm on 28.
Maybe,
Yeah, we see 28.
I would suggest that maybe if you turn off your camera, it would improve just during the talk, if you don't mind, of course.
Gary, if you want, you can change the browser, the web browser. If you started with Chrome, you go to Safari. If you started with Safari, you go with Chrome. And we are going to wait. I think it's better.
Well, let me try turning off the camera. That's easier. Okay.
Okay.
And I go back. Okay. So we're on slide 28.
Yeah.
The lower the delta AIC, the better it is. And so there's and usually if there's a difference of 6, it's strong evidence. So here there's very strong evidence that there's excess mass in the center. And then my student had the brilliant idea, Eduardo had the brilliant idea of trying to have an extended mass. And with the extended mass, it was even much smaller. So there was very strong evidence that there is extended excess mass in this cluster of a few % of the globular cluster mass and size. Okay? So he called this a CUO, Central Unseen Objects. I don't like so much the name, but that's what we use. Okay. So I asked him, what if you put a prior that the excess mass is not small, but just like the cluster? So he tried, and he again found a very small excess mass, but non-zero. Okay, so this was very nice. These are goodness of fits. It's not very interesting because goodness of fits plots involve binning, so they're not great. But basically, if you go from the no dark component, the red points, which are the data, go above the models. So you need something inside. And if you take a black hole, then the rise is it occurs too much inside, and so you really need to have this extended mass to have better fits. So these were conclusions of robust to everything we could think about. Okay. And these are the best fit density profiles, which indicate that the main sequence stars coexist with this central unseen objects. Okay, but now the question is, slide 34, what are the central unseen objects made of? Okay, slide 35, they could be made of something that is heavier than the stars of the main sequence that we observe. They cannot be made of M dwarfs, because if they're deep inside, they must have fallen inside.
You are still, excuse me, Gary, you are still on slide 34. We see still slide 34. And I think you moved to 35.
Do I have time to switch to Chrome?
Yes.
Yeah, go ahead.
Yes, sure. Go ahead, please.
Yeah, in fact, I should have done this because I wrote to myself I had to do this on Chrome. Okay. Okay, I'm on Chrome. I'm going to kill the Safari. Stop presenting.
Now you're mute, Gary.
Your mic is mute, Gary. Microphone is muted.
Or I'm unmuted.
Now we can hear you. Okay.
Okay. Can you see slide 35?
Yes.
Yes.
Thank you.
I'm sorry about that. So what I'm saying is that because there's an inner excess, there must be heavy objects that fell into the center by dynamical friction. And so we have to think of stars that are more massive than the main sequence stars, which are all less massive than 0.77 solar masses. So we can think of heavy white dwarfs, neutron up to 1.4 solar masses, neutron stars, and stellar mass black holes. So then I asked myself, okay, well, what is the fraction of mass in each? And for this, I did a very simple calculation. I integrated the initial mass function times the remnant mass given the initial mass. So this you can find in the literature, which is shown in the plot. And so when I do these integrals, I find that almost 60% of the mass should be in black holes, in stellar mass black holes. In fact, you can even expect what's the mean mass, typically 20 solar masses, typically 60 of them. Okay. So I say black holes dominate unless they escape the cluster. And now there are good reasons to believe that stellar mass black holes might escape the cluster, because this cluster has a steep density profile in the center. So the density of stars is high, so there's a lot of three-body interactions. And when you have three-body interactions, we know that hard binaries, that are binaries that are involved with a third star where the triple system is bound, well, then what happens is that the third star, when it comes in, might be an exchange of stars, but the star that goes out will typically go out at the speed of one of the members of the binary. And the binary, because it's hard, the two stars that are close to each other are turning around very fast. So the third object gets kicked out faster than it came in. So by conservation of energy, the binary gets even tighter and thus harder. Okay, that's one thing. But another thing which took me a long time to realize is that not only the third star gets kicked out, but by conservation of linear momentum, the binary will recoil and in the opposite direction. Okay. Which is what I tried to show in this figure here. So the black would be the black hole binary, and by recoiling after many three-body interactions, it will pick up so much velocity after square root of n. After n interactions, it will pick up square root of n times the typical velocity kick of the binary, and that will allow it to escape the cluster. Okay, and there's been a lot of tests of this in n-body simulations. So the other thing is that when black holes merge, the mergers tend to be of unequal masses, and that gives anisotropic gravitational wave emission, and which means that the gravitational waves, they carry linear momentum, okay, which is something weird to conceive. And so if they carry linear momentum, then the merger remnant will carry the opposite linear momentum, so it will also get a velocity kick, and the speeds are huge. Okay, they're in hundreds of kilometers a second. If not thousands, compared to the escape velocity of the globular cluster. So the black holes escape. So there's two ways of escaping them, by black hole mergers and by three-body interactions. The three-body interactions take more time, but if you work out the time scale for a binary black hole, for the black hole to sink in the center, a single black hole to sink in the center is just a mega year, all right? So they don't sink in the center, and so we think that these three-body interactions are preventing them from doing so. So we started a new analysis with our friends at Hubble Space Telescope, or Space Telescope, And they told us we can give you better data now. We have a longer baselines, so better proper motions, and we have better calibration. And so we were very excited. So we did this, and we did this for 2 clusters. One core collapsed, the same one, 6397, and one non-core collapsed, 3201. And now we're using Gaia EDR3. So as I will show you, this is better. And then we have this HST revised data. Okay, so these are the 2 clusters, and these are the surface density profiles, and one can see that that 6397 has a much higher surface density, and since the 2 clusters have similar, they have a similar core radii, if you wish. So the 3D density in 6397 in the inner regions is much higher, maybe 10 times higher than in 3201. Now I'm showing again this is the plot I showed you before. Can you see slide 39?
We can.
Oh, great. Okay. So now I'm showing you on the same scale. Okay, it took me a while to get these scales right. At the same scale, I'm showing you the new data. So first, if you look at the red points, and I put a pink arrow, so they're like pushed to the right. So we gain 1.5 magnitudes or 1.2 magnitudes compared to Gaia DR2 with Gaia EDR3. So that's great news. In other words, in proper motion space, we gain maybe a factor of 40%. On the other hand, the HST data gets worse, okay, because it's better calibrated. They discovered systematics in the proper motions versus position. They're little waves. In Gaia also they're waves. And in fact, the Gaia data, as far as I understand, are not corrected for the systematics. But I presume the systematics are small. But in HST, they're pretty big, okay? So it's a big letdown. I was very disappointed by this. Okay, so in fact, our data is worse, but we have to live with this, right? So anyway, so we redid the analyses. And so for 6397, so it's a little bit less anisotropic. So now we think that there might be slight radial orbits on the outside, but it's consistent with anisotropy at the 1 sigma level. And for 3201, the error bars are bigger because the data is not as good. It's a bit, it's a higher distance from us. And it's consistent with isotropy, okay? And then, okay, I'll show you these boring tables just to show you that if you select on the Bayesian evidence AICC, you want to take the smallest number, all right? So the most negative number. And so the central, so the extended excess mass, the CUO, central unseen objects, is the best for 6397, like before. But the evidence for the excess mass is very, very strong, but we cannot really rule out the intermediate mass black hole. Okay, the difference of 2 is not significant. Okay, it's good to talk about. It's something that the statisticians say you should talk about it. It's marginal evidence. And then for 3201, it goes the other way. The best evidence is for the intermediate mass black hole, but again, it's marginal. So so Eduardo had the great idea of saying, okay, why don't I compare the results to the results I would get from mock data. Okay, so what he did is that he built mock data using 4 different assumptions, okay, for the mock, which I will show here. So on the left, the mock was no central mass, and then one was intermediate mass black hole, one was a CUO, and one was both. Okay, and so he built these mocks, and then he asked himself, can MAMPOSSt recover these mocks? But he did it where the MAMPOSSt assumes a certain one of these 4 models, and the model he assumes is a CUO. And the reason why he assumes a CUO is not that he believes it, is that by assuming a CUO, you can look at the marginal distribution of the size of the CUO, this RCUO, the lower right plot in each one. And what you see is that if there's a black hole in the second plot here, I'll show my arrow here. So the data is always in blue, okay? And the data is actually the same everywhere, okay? Even though it's scaled differently. So the data is in blue, but when you analyze the mock, it's in red, okay? And what you see is that if you have a mock with an intermediate mass black hole and you assume a CUO, then you'll find that the size of the CUO is very small, okay? But if you assume that there is a CUO, then you will find an extent. You'll see that there's a peak in the distribution, which is almost the same as what you observe, okay? And then if you assume both, it's a bit more complicated. But anyway, so this tells us that using the marginal distribution of the excess mass radius is a good way to distinguish intermediate mass black holes where the distribution will be towards very low values, and a true excess mass that is truly extended, excess mass, which will show you a peak. Okay, so for NGC 6397, we think there's strong evidence for extended central mass. For NGC 3201, the data is much worse. So if you compare the second plot with IMBH, the red curve does not show a maximum. For the CUO, it does show a maximum. So and the data shows a maximum. So the data resembles better the CUO than the IMBH. Even though the Bayesian evidence favors the IMBH, we think that this particular part of the likelihood, which is the CUO radius here, is the most important. Okay, and so we think we have mild evidence for the presence of also an extended mass in 3201. And then I'll tell you whether this is reasonable. Okay, so weak evidence for extended central mass. So the way to find out whether it's reasonable or not is that we collaborate with Carl Kremer at Caltech, who's involved in this large collaboration led by Fred Razio at Northwestern University near Chicago. So they do Monte Carlo n-body simulations. That is, it's not pure n-body, because they cheat on the distant encounters, and they add extra physics for the black holes and for stellar evolution and for natal kicks of supernovae and the black holes and gravitational wave kicks. And by doing this, they already analyzed these clusters, but they redid it for us using our parameters. And this is what they find. Okay, so for so let me start with 3201. So 3201, what they did is that they looked at the different snapshots of their simulations, and they asked themselves, which snapshot matches best the projected phase space of the observations? Okay, and they select that that snapshot, and then they ask, what is going on in that snapshot? So here are the 3D mass profiles, and what you see is that in the inner regions, the blue curve is dominating. Those are stellar mass black holes for 3201. Whereas in 6397, what's dominating are white dwarfs. Okay, the red and green are two types of white dwarfs. Okay, the red are very extended, so they kind of follow the stars, but the green are very interesting because they're really a centrally located system. These are the oxygen, neon, magnesium white dwarfs. So we have two completely different conclusions from the simulations on what we're seeing, but at least the simulations tell us we should be seeing an excess mass. Okay. And so they confirmed that the excess mass is not a single black hole, but a collection of stars. And these stars are stellar mass black holes for 3201 and white dwarfs for 6397. Okay, and I'll try to explain why in a second. Okay, and if you look at the typical masses and sizes that they predict, they match very well. Now, so let's talk about evolution scenarios. So in the early days of a globular cluster, the massive stars will turn supernova and might turn black holes, okay? And that can go very quickly, okay? And then the black holes will rapidly segregate to the core, okay, by dynamical friction, okay, against the other stars. Fine. And then for the core collapse globular clusters, 3 body encounters will be important. Okay, so for the clusters like NGC 6397 that have steep inner density profiles, there's going to be so many stars that the black holes might form binaries. All right, so you might form binaries by 3 body encounters, as I show in this illustration. And once you have 3 body encounters, then you have binary black holes. And once you have a binary black hole, then when you collect it with when you interact it with another star, then the black hole will get tighter, the star will get ejected, and the black hole will get kicked the other way by conservation of linear momentum. So eventually they escape, as I said before. And this team of Fred Razio, here led by Rodriguez 21, they argued that in fact most LIGO-Virgo GW events, if not all, might be the effects of the mergers of binary black holes that were formed in globular clusters, but that escaped before merging. Okay, so they escape and they're outside the globular clusters, even though they might not be far away. Okay. So this explains the difference between 6397 and 3201. 6397, it has such a high star density in the center that the black holes cannot remain. They form binaries and then they're kicked out by repeated velocity increments by conservation of linear momentum in the three-body encounters. And this is what you see in the Monte Carlo dynamical simulations. On the other hand, NGC 3201 is a globular cluster that is non-core collapse. So there's not enough. They're not sufficient stars to have three-body encounters with, and so the black holes live their lives and they stay around. Okay. So to continue, this combination of mass modeling that we've done with the Monte Carlo dynamical simulations, they give this consistent results. And to finish, we have possibly detected an IMBH in one cluster. And so this is still under embargo. We cannot talk about it. We haven't submitted the paper. And it also lies, and it depends on the one star. Okay, so this one, but because it's Bayesian, the Bayesian analysis has the probability distribution, whether it has a probability distribution for the star that is the most central star. So this is a third cluster, okay, which I'm not allowed to name. But there's in this third globular cluster, there's one star close to the center, which has a very high proper motion. And so is it a star that is indeed pushed by the velocity field of the intermediate mass black hole, or is it an outlier along the line of sight? This is something that is difficult to predict, but it lies in the proper motion space where the globular cluster is. Okay, and so the perspectives are to analyze more globular clusters to see whether some have intermediate mass black holes after all. And so I think I'm done. I am done. So thank you very much, and will be glad to listen to your questions and to answer them if I can.
Thank you so much, Gary, for such a clear talk despite the technical issues. But in the end, I think it was great. We could understand everything that you explained to us. So to begin, we have a question by Professor Elizabeth. Go ahead, Beth.
Oh, thanks, Gary, for the very interesting talk, and the results are really very interesting. So your results point to the fact that probably globular clusters are not the best site to host intermediate black holes, right? Intermediate mass black holes, right?
Yes.
Because at the end you have dynamically, it's almost impossible to keep them growing by merging, increasing merging, right? But
yeah, the problem is that if they grow by mergers, then the mergers will kick them out by this anisotropic gravitational
they
wave.
end up to be, they are kicked outside. Yeah.
Unless, if I can interrupt, if you can manage to make them big, and so if they're already 500 solar masses and they merge with a 10 solar mass black hole, the ratio of 50 might be large enough to make the velocity kicks small and not kick them out. But how do you get them to 500 in the first place, right?
Yeah,
so,
it would be very hard. Yeah, interesting, anyways. But then you concluded saying that you intend to increase the sample of observations, more globular clusters in search of intermediate mass black holes. Do you have plans for this, for continuing this search, or do you have a specific sample for this, or we can conclude from these results that you showed that we should really search for intermediate mass black holes in dwarf galaxies rather than still pursuing this idea on globular clusters? What do you think?
Well, I'm mixed. Because of the third globular cluster, which may have an intermediate mass black hole, and we understand how it can form, but we don't understand how it can survive. And but if we have the evidence of it's weak evidence, but we know we will publish it. We will. So Eduardo has to submit his thesis pretty soon in July, but he's well advanced on the paper, so I think that it should be submitted in a month, and we'll see how it goes. And then, yes, we will continue collaborating with the people at Space Telescope who have fantastic HST data. And in fact, they're proposing to us also to, I think it's for the third globular cluster, they have more data. And so they want to give us more data so we can analyze it better. But the more data they have is that they have a lot of data, but on the short baseline. Okay, so we're using a long baseline, and they're giving us a short baseline with a lot of data. So it might reduce the systematics. I don't know. We cannot figure out. So they're reducing it now, and then they'll give it to us. And otherwise, they have other globular clusters for us. Okay, so we're going to do 2 or 3 other ones. But the further we go out, the more the uncertainties are preventing us from getting a strong conclusion. But it'll be interesting at least to see. Right now, I've shown you one globular cluster core collapsed and one that's non-core collapsed, and we reached opposite conclusions. It'll be interesting to see whether we can confirm this with extra globular clusters. Okay, and maybe we'll find also that the mass profiles depend a little bit on the orbit of the globular cluster around the Milky Way. I don't know, so we can test that, because we think we know the orbits now from the the bulk proper motions of Gaia. Okay, there's some slight differences between the mass modeling, and in fact, people are realizing only now that you should not take the Milky Way as the potential. You should take a system with Milky Way plus LMC. Okay, because LMC weighs about 10% of the Milky Way, and so it's pulling the Milky Way towards it a little bit. Okay, and so. This is so to do it right, we should add the LMC in the model.
Yeah.
Thank you, Elisabetta.
Oh, you are welcome. Well, I have to thank you for this nice talk. Thanks a lot.
Thank you, Betty, and thank you, Gary. Now we have a question by Marcelo. You can go ahead, Marcelo.
Okay, hi. Can you hear me well?
Yes.
Okay, good. Thank you, Gary, for this very nice talk. You mentioned that black holes, they escape through three-body dynamics. They can escape from the globular cluster. Do you have any estimate, or do you know any estimate of how many black holes may escape in a globular cluster, for example? And how could it impact in the total mass budget of a galaxy?
Ah, that's a good question. Well, one can work it out, right? So in a cluster like core collapse cluster, like the first one, 6397, in fact, we did work out, what would be the fraction of the excess mass already in the center. So if you just consider that region, so I said there would be 57% of the mass in black holes, but since we think that there's no black holes or very little left, and we know the mass, which is about 1,000 solar masses, then we could conclude that, and we know how many black holes there would have been, given that there's 1,000 solar masses and the black holes are 60%, let's say 2/3, then there should be double that have escaped. So we think that 2,000 solar masses in black holes must have escaped. And so 2,000 compared to 100,000 is not much, it's 2% of the mass of the cluster. But that's only for the inner regions. For the outer regions, well, there'll be less three-body interactions, so the stellar mass black hole should survive, I think. And so, yeah, I think the order of 2,000 solar masses of black holes probably escaped. Let me write down my answer before I forget. Okay. And these black holes, they're escaping often as pairs, and they might, once they escape, emerge and form gravitation and emit gravitational waves.
Okay. So there's 2,000 solar masses per globular cluster.
So now, so how many escape? Since the typical mass of black holes should be about 20 solar masses, how many should escape? About 100.
Mm-hmm.
Or 50 pairs.
Thank you. Nice, thanks.
So you could say, wow, this cluster might cause 50 gravitational wave events. Yeah, but the probability that we pick one is very small.
Yeah.
For a given cluster.
Okay. Thank you, Marcelo, and thank you, Gary. And now we have a question by Ranieri. Go ahead, Ranieri.
Hello, can you hear me?
Yes.
Hi, Gary. Thank you very much for this nice talk. I just have a quick comment about your results on NGC 6397. That your results are compatible with the gamma ray emission that we observed from this cluster a few years ago. So from the gamma ray data, we discovered that the binary systems in the core of these clusters are disrupted or ejected from the cluster. So it was just this quick comment. So your results are compatible with the gamma ray data as well. And by the way, maybe this is something that you would like to use in the future, the Fermi data for this kind of analysis of globular cluster.
So first of all, before I forget, who's the first author and what's the year? Is it you?
Sorry?
Who was the first author of this analysis?
It was me. Yeah.
It was Menezes. What year?
Yes. 2019.
19. Okay.
Yes.
So yeah, I was not aware of this paper. Now, so what makes you think that the gamma ray, that the binaries are not there? Because if there were binaries, you would have bursts, and you're not getting bursts from the globular clusters. But Fermi
No.
Fermi does not have the spatial resolution, maybe, to
okay.
the globular cluster or not.
Yes. Everything that we do with Fermi is considering that the cluster is a point-like source. Mm-hmm. But the gamma ray emission from globular clusters, they come from millisecond pulsars that are originated in very close binary systems. So the gamma ray emission for this cluster is lower than it was expected by some relation that we have in millisecond pulsar astrophysics. So we have this relation.
Okay. And
the gamma ray emission from this cluster is significantly below what we would expect. So, and the conclusion from the paper was that the binary systems in this cluster were disrupted or maybe ejected. That's why we would not see a strong gamma ray emission that would be originating from millisecond pulsars.
Okay, well, this is very interesting. What we did in the paper, in the first paper, is that we looked at X-ray binaries. So I'm going to cooler temperatures. Mm-hmm. And we found that the distribution of X-ray binaries was, given the data they had, was more concentrated than the stars, and was not that different from the cluster of unseen stars that we had found. Okay. So now that we think that that the black holes might have escaped this cluster, what's left is about 80% of mass in white dwarfs and 20% in neutron stars. So if these neutron stars have companions, then they'll make X-ray binaries, and they'll be more concentrated to the center than the stars because they're more massive. Okay, they originate from massive stars.
Yes, perfect. Dynamical friction. Yeah.
And for the millisecond pulsars, I'm not a good enough astrophysicist, but if it's pulsating, is it not a neutron star? Does it have to be a black hole, or is it neutron star plus black hole? What are millisecond pulsars physically?
Millisecond pulsars, they are formed from very old neutron stars. They were normal pulsars in the past, but it was so long ago that they lost the rotation.
Yes.
So by random interactions within the cluster, they form a closed binary system, and they start to swallow matter from the companion. As they swallow this matter, they speed up again, and they start to accelerate the particles again in the magnetosphere. And this acceleration is so much that they start to complete a rotation in milliseconds. That's why we call them millisecond pulsars.
But these are very old neutron stars, so they're not
very, very old.
So okay. So but they're not black holes.
No.
Okay, fine. Yeah, that's very interesting. Well, thank you very much, and we will read with pleasure your paper of 2019.
Thank you a lot.
Thank you, Ranieri, for the discussion. And just one comment, Ranieri, I didn't find your paper on the ADS, so if you could link your paper here in the chat, that would be useful. And now we have actually a question from Laerte.
Hi, Gary. Congratulations to you and Eduardo for this nice work. My question was actually motivated by the commentaries of the Ranieri. I wonder if it's possible to constrain this nuclear population with observations in other wavelengths. For example, in the UV or even in X-rays or radio. Have you explored this possibility?
No, I should have, but no, I haven't explored this very much. So can we look for populations of neutron stars, for example? Is that what you think, or white? So white dwarfs, with deep, we probably have deep enough observations with HST to pick up the white dwarfs that are not too close to the center, so that we can deblend them. Because the team of Harvey Richer in Vancouver have gone very, very deep for some globular clusters, and then they see a beautiful HR diagram with a very fine relation for the white dwarfs, and these are old papers of 2009 or something, or even older, and I was amazed at the quality of their work. And so going to Harvey Richer, we could probably just from HST data, particularly using low wavelengths filters with HST, as they did in the past, pick up the white dwarfs. For neutron stars, yes, so then we have neutron stars you can pick up in X-ray binaries. This is what I was alluding to. Baramanyan was the author of this paper that did in 2018, I think, 6397. And they found X-ray binaries, and we noticed that their distribution was more concentrated, given their minimum and the maximum, given their field of view, was more concentrated than the main sequence stars, which is what we expect. Okay, and it was roughly what we were getting for the central unseen object size. And then so that's the white dwarfs, that's the neutron stars, and then for the black holes,
yeah.
And then if you're lucky, you can do microlensing also. I don't know, but there are not that many field stars behind. But yeah.
Okay, and I would like to ask you another question. How reliable are these Monte Carlo simulations, N-body simulations?
I don't know. So the team is the people are very brilliant doing this. They're not using. There's a public code called N-body 6 and N-body 7 by Sverre Arses, which has a lot of extra physics included. So it's really tailored for globular clusters. But they're not using this code. So they did their own code. They developed it over the years. And I find that their papers are not very well written because they don't explain very well the physics of their code. And they have it in one paper, and even that one paper, it goes very fast. And And when we write about galaxies, we're not like that. We always explain what we're doing, and we don't refer to other papers for the important details. And and here, even for this other paper, they don't give all the details. So I'm a little bit confused by what they did, and so what I understand, I obtained it by just speaking to them. Okay, that's one thing. Another thing which bothers me is that I would like to have an analytical model for the rate at which black hole binaries pick up velocities by this linear momentum conservation. And so I've read the literature of three-body encounters, and I've been very disappointed because I don't think they're doing it right. All right. It's very presumptuous for me to say, because the people involved in this are extremely brilliant people. And they're not doing it right because they consider hyperbolic encounters. But the encounters are parabolic. Okay, they're not parabolic, they're bound. They're bound encounters. Hard binaries, by definition, are bound. So they assume that you have an unbound star, because they talk about impact parameter, right? And so they think in terms of collisions. These are physicists, okay, who started this. Pete Hutt was a physicist, so they think about this in terms of collisions and impact parameters. But in fact, they're bound. So they say, it starts with the velocity of with the velocity dispersion of the stars of a few kilometers a second, and then it's going to get kicked out with the velocity of one of the stars in the pair, on the tight pair, okay, which is huge, okay. But it's much more complicated than that, because in fact, for a bound orbit, it starts, the apocentric velocity will be the velocity dispersion, but the pericentric velocity will be already very high if it gets close, okay? So it's very difficult, and so then the kick that will come out, who knows what it will be, okay? It depends on the exact encounter, okay? And I cannot think of a way of doing it because I'm not clever enough, but nobody has done it. All I can say is that I'm not happy with what was done. I've written to Doug Heggie, who's God in this, and who's very friendly. And he said, read this book called Three-Body Encounters, or Three-Body Systems, by Valtonen. Okay, Valtonen and somebody else, two Finnish people. And Valtonen, he's also known for galaxies. But in fact, I discovered that Valtonen did most of his work on globular clusters. And the book is very detailed, but they don't do it. They only consider these unbound orbits. So I'm puzzled. I should write to Valtonen, but I think he's retired. But
okay, thanks.
Because if we had a hand-waving formula, then we can check the simulations. Okay. And,
Yeah.
Thank you, Laerti. And we have a final question by Professor Gaston.
Thanks, Gary. It was a great talk as usual. And I have a question. It's maybe you said that at the beginning, I may have missed, but how these two clusters were chosen? Are they far away or particularly isolated?
Okay, let me show you here. Let's see now, where was it? Where was it? It was here. Right? So yeah, we chose the clusters that had the minimum distance over velocity dispersion, because we know that will give us the minimum, the lowest errors, proper motion errors. Okay, relative to the velocity dispersion.
And in this case,
so these are the clusters that have the minimum values, and then we crossed out those that are rotating. So that left us with these guys, and so these three of them we haven't done, which is 6544 M4 and 6752. So we intend to do them because the HST people, they have the data, but they haven't finished calibrating it. And so I hope I answer your question.
Yes, and then I have an additional one.
Oh, they're all close, So you see 2 kiloparsecs, and the other ones are typically within 5 kiloparsecs because we want to minimize d over sigma d.
So that was what I was thinking about, and the fact that they are close, that means that those clusters may be crossing the Milky Way disk, right?
Yes, that's a very good point. So 6397, for example, its orbital time is less than 100 mega years. All right, so it had quite a few orbits, and it's crossing the disk. Its orbit is very strange. Okay, so it's crossing the disk twice at different distances from the center of the cluster, at very different distances from the center of the galaxy. Sorry.
Mm-hmm. And then, okay, no, and the problem is if they are crossing the disk, wouldn't they be perhaps heated by tidal interactions with the disk? And this tidal interaction, couldn't it mask as a signature for this unseen objects that you are detecting in those clusters?
Okay, well, that's a great question, Nestor. So, so there are a couple of things, right? There's tidal effects from the disk, okay, and then there's heating, okay. In fact, the tides do heat, okay, because the tides will give you energy, right? And so one thing we did, we asked, do we see tidal effects on these clusters? And so one exercise we did is we plotted, I'll put it in the paper in a second. Papers. Oh, so here's the paper. So we plotted over here. Let's see what it is. Oh, I can't see it. Oh, I'm sorry. I'm making you waste your time. Here it is. So you can plot the mean velocities and the velocity dispersions of the two components of the line of the plane of sky dispersion. So this is the plane of sky pointing towards the center of the cluster, and plane of sky perpendicular. And so two funny things happen, and which is probably due to tides. One is that on the outskirts, the mean plane of sky motions start diverging slightly, okay? Whereas here they're within the error bars, but here they're no longer within the error bars outside, but inside they are. And secondly, the velocity dispersion profile suddenly starts rising at the 1,000 arc seconds, okay? Which is 20 arc minutes, okay? And so we decided to stop our analysis at this green vertical line, okay? Because then we're worried about tidal effects. So the tidal effects are strongest outside, right? Because the tidal forces are proportional to the distance to the center. So presumably the heating from the tidal effects will also be there, okay? And so the heating in the inside, I think the inside don't feel so much the tidal field of the galaxy. So that's one thing. The other thing is that the tidal field of the galaxy, well, no, I was going to say something stupid, but yeah, no. I was going to say the gravitational potential of the galaxy is the sum of that of the components of the galaxy. And so you have the disk, the bulge, and the halo, the dark matter halo, and the bulge is not. A lot of people think that we don't have a bulge, that we have a thick disk that mimics a pseudo bulge. And but anyway, if you look at Binney and Tremaine, there's a nice plot of equipotentials of a disk plus a halo compared to the and what you see is that the equipotentials are only slightly pushed in, and so but that's potential. So if you look at potential gradients, it will be stronger. So but anyway, there will certainly be tidal effects. So a lot of people talk about tidal shocks when you will cross a disk. Mm-hmm. Okay, so here you cross it twice in 95 million years. All right, so this is important. And I forget where in 6397 it was in its orbit, whether it was, I think it was just coming out the disk now. I'm not even sure we mentioned this in the discussion, but these are very interesting comments. And so could it, if it heated the center, why wouldn't it heat up the other regions? Okay, so what? So it should heat up the other regions, so even more.
Okay.
And the n-body simulations done by our friends, our colleague at Caltech, Kyle Kremer, and the team of Fred Razio in general, they assume, as far as I remember, they assume no tides, that it's just an isolated cluster, right, for simplicity. I might be wrong, but they write a lot of papers. You know, they are very hard to follow. They write 5 papers per year, and when we wrote this one, they immediately wrote one saying it cannot be black holes, it must be white. They wrote 2 in less than 3 months after this one came out, saying it must be white dwarfs. And basically, we made a press release talking about the black holes, and we kind of overemphasized the black holes. But if you look at the abstract, we say we show that stellar mass black holes should dominate the mass unless more than 25% escape from the cluster. And their mergers in the course could be important source of gravitational wave events. So this we're completely wrong, because now we think that the mergers occur outside. So now we think we understand that they do escape in this cluster, and that the gravitational wave events come from outside. So their cluster, they would be formed by the gravitational wave events would be caused by black holes formed in the cluster, but which have already escaped.
Okay.
So
thanks. Okay.
This was a little bit badly worded.
Thank you, Professor Gastão. Thank you, Gary. I would like to thank you once again, Gary, on behalf of the department.
If you can hire Eduardo Vitral one day, you should. Okay. So
that's with Gastão.
Yeah. So he has a lot of qualities. He's been my most productive student, and he might have he should have 7 papers by the end, of which 6 are first author. No, 5 are first author, or maybe 1 less if one doesn't get past the referee, because he has problems with one referee. Well, I'm not involved in it. And perhaps 1 more if I finish the paper where I'm first author and he's second author, which is on writing a description of MAMPOSSt-PM, including something which we didn't include, which is the proper treatment of the covariances between the RA and DEC proper motions. Okay, and that's a lot of math, and it's driving me crazy. But okay. I think I come to the end of it, but now I have to test it and write it up.
All right. Thank you, Gary. I think we can finish the transmission. Richard.
So thank you so much for your patience, and especially that I made the mistake of starting with the wrong browser. And it was a pleasure to be virtually in São Paulo, and I hope the next time I will be in São Paulo physically.
Yeah, we hope to.
Yes, thank you. So best wishes, stay safe, and oh yeah, I have to go home because in 20 minutes there's the presidential debate. Okay, so I don't know if you
good luck.
Yeah,
we have
good luck with that.
we have a second round of our election on Sunday.
Yeah, the second round, yes, in France. Yeah.
They do have debates in France.
Good luck. Yeah, I think the world needs,
There was no debate between Bolsonaro and what's his name?
Haddad.
Haddad. Actually, Lula.
Well, now this time will be Lula, but last time there was no debate.
Oh yeah, there was no debate. Yes, and we are immersed in this man. Let's hope for the best in France as well this time. Mm-hmm.
Yeah, I understand what you say, and I perfectly agree. So it's
yeah,
we're coming to a stage where you have the populists against the others, and the others are not always reasonable. And I personally can live with the current president, but some people, hate him. Okay, and so some of them are. So some people who I know, they're hesitating. Who should I abstain in the current election? Okay.
Macron, I think is less worse, right?
Yeah, for me, it's like orders of magnitude. Okay, less worse. And so I talked to someone, a colleague today, and so he's left wing, and so he cannot imagine voting for Macron, but because he said. So I asked him why. He says because if Macron comes, then you can be sure that in the next 5 years we'll have Le Pen. I say, okay, well that solves the problem. If you think Le Pen will come if Macron is elected, then you should vote for him, because otherwise you'll have Le Pen right away. You have 100% of chances of getting Le Pen right away if you don't vote for him. If you don't vote for him, well, if the country votes the other way.
Right.
And whereas otherwise, you don't know what's going to happen in 5 years.
Yeah.
I hope I convinced him.
Yeah. It would be much worse.
We have a hand raised by Elvis.
Yes. Is there time for just a last question?
Yeah, sure.
So Gary, thank you very much for the presentation. I was very interested because some time ago I was speculating about the existence of excess mass in the center of a globular cluster that I worked on my master's. Actually, I sent 2 mails to Eduardo on February of last year, but maybe they got lost in his mailbox.
He didn't answer?
No, maybe. I don't know why, but he didn't answer.
Send it again to him with a copy to me.
Oh, all right.
Even if it's in Portuguese or translated, that would be even better.
No, I just sent it in English this last time, but
no, because Eduardo is very good at answering emails. It might have ended up in his spams.
Okay. Well, I'll say it again so I can copy you also.
Mm-hmm.
But it's about the cluster that I worked at, and I spotted some weird stuff about that, and I imagined could be some IMDH or something like the maybe more than one, as you stated now. And I said, okay, maybe just one cannot explain, but some of stellar mass black holes at the center may explain that. Those features.
So I don't understand. So what made you did you do some analysis to think about the presence of IMDHs? Is that it?
Yeah, actually, I talked to Professor Gaston some time ago about that. We started looking at that, but the main thing that caught my eyes was an X-ray emission at the center and diffuse ultraviolet emission in the whole cluster area. And I said, I never saw this in any other cluster. And
this was in which cluster?
NGC 6522. It's a bulge globular cluster. It's the Bades window.
Bade window?
Yeah.
Oh, so it's a cluster close to the galactic center.
Yes.
Galactic center. I'm taking notes. Okay. Did you write up your master's project?
Yeah, actually, I was making a chemical analysis of the giants, and then I put that on my thesis as an appendix, stating that I found that things and maybe black hole in IMDH may explain that, as Cassisi once argued about IMDH may trigger different formation events on a globular cluster. And I said, well, that can explain some things, because I found metallicity inhomogeneities in that cluster, and I ended up not publishing that kind of inhomogeneities, but because of this conflicting interests between me and my previous advisor.
But so you found that the main sequence was had a width that might show different chemical populations?
Maybe they were just not a main sequence. It was on the giants.
Oh, on the giants, yes, of course.
Yes.
Sorry, you mentioned giants. So in the giants,
not clear. It was
so the red giant branch. Because you have to worry about differential reddening.
Mm-hmm.
Okay, and especially if this cluster is in the Bades window, the extinction is still not zero. It's probably It's probably higher than the ones I'm looking at. So there might be changes in the extinction across the field. Okay, and so some parts of the globular cluster might have different extinctions than others. Okay, and so that will, if you take the globular cluster as a whole, then your color magnitude diagram will be thickened by the different metallicities that you're picking, the different reddenings that you're picked up. And so there are ways to correct for that. And so you can try to even make an extinction map using the globular cluster stars, because you have a lot of stars. Okay, and then once you correct for that, then you can look at the chemistry.
Yeah, actually, we were doing high resolution spectroscopy using UVs and GIF.
Ah, this is interesting. Let me write this down. High resolution spectroscopy using what instrument you said?
Flames.
Flames or UVs.
Yeah, both.
Flames and UVs. Oh, very interesting. Okay, well, this is very interesting. Too bad you didn't publish. Well, of course, you know, when you're a master's student, you don't think you're publishing all the time. But...
Yeah, actually, there was a paper, but the analysis ended up being done in a way that I didn't agree.
Ah, and so the paper, are you Carvalho or are you Cantelli?
Sorry?
When you write your papers, which name do you use?
No, I use it Cantelli.
Cantelli.
Yes.
Okay, let me take a look. Harry Elvis. Ah, yeah, I found quite a few. Okay. And so what year was this?
Sorry?
What? Oh, yeah, here it is, 6522, number 6.
Yeah, there are some.
Ah, it was
the last
Beatriz.
one is these results that I particularly.
Eduardo Vitral, Vanessa Hill, Anita Gomez. Yeah, I know quite a few people in your team.
But that was my master's work. I ended up doing other thing in the PhD.
Okay, so yes, so you said paper in 2014. Paper in 2014, Babu et al. I'm writing down, but I didn't agree with all the conclusions. That's what you said. But I didn't agree with all conclusions. Okay.
So maybe
Beatriz is not here to debate on this. Okay, great. So I'm going to stop presenting. Yeah.
Yes. Okay. I'd like to thank you again, Gary, for giving this talk, for your time, your.
Oh, it's great to meet you all. It's great to meet you all. And now I'm going to rush home to watch the debate. It starts in 20 minutes, so it takes me 10 minutes to get home, so I still have time.
Great. Yeah. Thank you a lot.
Bye-bye. Okay. Thank you so much.
Okay. Bye-bye.
Bye-bye.
Thanks a lot. Bye, Gary. Thank you very much.
Looking forward to meeting you again quickly. Bye.
Hopefully. Bye-bye.